Welcome to your Algebra 2 10.5 lesson on the probability of independent and dependent events. So what does it mean to have independent events? Well, two events are independent if the occurrence of one has no effect on the occurrence of the other. In other words, if you know one event occurs, the probability of the other event occurring doesn't change. So one of the things that we can use with independent events, if we know A and B are independent from each other, then the probability of A and B is going to equal the probability of A times the probability of B. And if we have more and more and more independent events, we can just keep multiplying their probabilities together. Okay, so for a fundraiser, a class sells 150 raffle tickets for a mall gift certificate and 200 raffle tickets for a booklet of movie passes. You buy 5 raffle tickets for each prize. So what is the probability that you win both prizes? Well, first of all, are these events independent? Well, yes, because you've got separate sets of raffle tickets. You've got gift certificate tickets and you've got raffle tickets for the booklet of movie passes, and you've bought 5 of each. You bought a total of 10 tickets. So we're going to use our formula. The probability of A and B is equal to the probability of A times the probability of B. And so you have a probability of 5 out of 150 for winning the gift certificate and 5 out of 200 for winning the movie passes. You can reduce them down to 1 out of 30 times 1 out of 40, and so that gives you 1 out of 1,200. So that is your answer. The answer is B. Okay, go ahead and do the guided practice and come back for example 2. So now we're going to move to 3 events. In a BMX meet, each heat consists of 8 competitors who are randomly assigned lanes from 1 to 8. What is the probability that a racer will draw lane 8 in the 3 heats in which the racer participates? Okay, so there's 3 events. Since each drawing is random, or each assignment is at random, they should be independent of each other, and so the probability of A and B and C is going to be the probability of A, which is getting lane 8 in the first race, so that's 1 out of 8. Probability of B is still going to be 1/8, and probability of C for that last race is still going to be 1 out of 8 as the probability of drawing that particular lane. And so we get a product of 1 out of 512, which is about 0.00195, so about 2 times out of 1,000 that would happen. Let's look at using a complement along with what we've learned in a situation where we have music. While you are riding to school, your playlist randomly plays 4 different songs from 16 songs. What is the probability that you will hear your favorite song on the playlist at least once during the week? Well, the probability of hearing your song is going to be 1 minus the probability of not hearing your song to the fifth power. And so the probability of not hearing your song would be the playlist choosing any 4 songs out of the other 15 that aren't your favorite, divided by the number of combinations where the playlist picks any 4 songs out of all 16, including your favorite. So not hearing your song on a given day, that probability is going to be raised to the 5th power because that happens 5 days in a row, each day being independent of the last day. So it's 15 choose 4 over 16 choose 4 to the 5th power, and then we're going to subtract that from 1. Okay, so the probability of at least one hearing your song at least once during the 5-day week is 1 minus the probability of never hearing your song all week long. And so the probability of hearing your favorite song is going to be about 0.763. So roughly a 3/4 chance that you will hear your song at one point in the week. Okay, so go ahead and do the guided practice here and then come back to the video. Go ahead and pause. Okay, welcome back. Now we're going to talk about dependent events. 2 events are dependent if the occurrence of one affects the occurrence of the other. In other words, if you know one event occurs and that changes the probability that the other event occurs, then they're dependent on each other. Okay, so if A and B are dependent events, then the probability both A and B occur is the probability of A and B, and that equals the probability of A times the probability of B given A. Okay, so there's that little line segment right there, and it's read given, where the probability of B given A is the conditional probability of B occurring given that A has already occurred, and is read, as I said, probability of B given A. Okay, so let's look at a weather example. The table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate the probability that a future tropical cyclone is a hurricane, and B, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So for our first solution, the probability of it being a particular storm being a hurricane is going to be the number of hurricanes over the total number of cyclones. So the total number of hurricanes, we need to add the number of hurricanes from the northern hemisphere and the number of hurricanes in the southern hemisphere. So 545 plus 215 is 760. And then we're going to divide that by the total number of cyclones. So we add everything all together. And so we add all the numbers and we get 1,575. Okay, so 199 plus 398 plus 545 plus 18 plus 20 plus 215 is 1,575. So out of those 1,575 storms, 760 were hurricanes, and so that probability is about 48%. Okay, so about 0.483, a little under half. Well, let's look if we're just talking about the northern hemisphere, okay? So this time, we're going to do the number of hurricanes in the northern hemisphere, so 545, and that's going to be divided by the total number of cyclones just in the northern hemisphere, okay? Because our world is shrinking to just the northern hemisphere here. And so this is the probability that we have a hurricane given that the cyclone is in the northern hemisphere. So we add 199 plus 398 plus 545, and we get 1,142. And so we have 545 over 1,142, and that is approximately 0.477. Okay, so let's compare independent and dependent events and see how just subtle changes can give us a different scenario. You randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is not a heart and the second is a heart if you A, replace the first card before selecting the second? So you get the first card, note what it is, put it back in, shuffle your deck again, and so in both the first draw and the second draw, you've got all 52 cards. For part B, you do not replace the first card. So that means that after you draw your first card, you just put it to the side. So on that first draw, you had 52 cards, but now you only have 51 cards. Okay, so probability of, the event A is that the first card is not a heart, and event B is the second card is a heart. Okay, so if you replace the first card before selecting the second card, then A and B are independent events because the probabilities are not changed based on whatever you get on the first draw. So our probability of A and B would just be the probability of A times the probability of B. There's 39 out of 52 ways to not be a heart. Okay, that's our diamonds, clubs, and spades. So add all that up, you get 39 out of 52 cards. And then for our second, the probability that we do draw a heart then would be the 13 hearts out of all 52 cards. And that multiplies and reduces to be 3 out of 16, which is about 0.188. All right, so there's just one little difference for part B, and that is we don't replace the card after we draw it. We draw our first card, note what it is, and put it to the side, and then we only have 51 cards left. So these would be considered dependent events. So the probability of A and B is going to be the probability of A times the probability of B given A. So for the first draw, nothing changes. It's still 39 out of 52 because you have your full deck there and there are still 39 cards that are not hearts. But now when you go to do your second draw, there's only 51 cards left in the deck. You still have all 13 hearts because the first one was not a heart. So our numerator doesn't change. And so we get 13 out of 68 once we multiply and reduce, which is about 0.191. So the probability of drawing a heart on the second one goes up just a little bit because our denominator went from 52 to 51. Okay, go ahead and do the guided practice. Pause the video, and we will go over those in class. Let's look at example 6. You and 2 friends go to the same store at different times to buy costumes for a costume party. There are 15 different costumes at the store, and the store has at least 3 duplicates of each costume. That's an important detail because that means that it's feasible that all 3 of you would get the same costume. What is the probability that you each choose different costumes? Okay, so the probability of A and B and C is the probability of A times the probability of B given A times the probability of C given A and B. So when you go to the store, or whoever goes first, okay, we'll say it's you. There are 15 out of 15 costumes you can choose without worrying about having gotten the same costume someone else did. Now, there are still 15 choices for your first friend that goes to the store, the second person. But if we're looking at the event where everybody has a different costume, so there would be 14 options for the second friend to pick from for y'all to have different costumes. When the final friend goes in, 2 out of the 15 have already been selected, so they only have 13 out of 15 options remaining. And so that comes out to be 182 over 225, which is about 0.809. So a little over 80% chance y'all are going to pick different costumes. All right, let's do a multi-step problem. Using observations made of drivers arriving at a certain high school, a study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. So that's a conditional probability. Under the condition the adult's wearing a seatbelt, a high school student will wear his or her 66% of the time. 26% of the time when the adult does not wear a seatbelt. So another conditional probability. Under the condition that the adult is not wearing a seatbelt, there's a 26% probability that the high school student will be. So what is the probability that a high school student in the study wears a seatbelt? Let's go ahead and make a tree diagram. We did that before when we were counting. This time we're going to include probabilities. Okay, so in a car, either the adult has on a seatbelt or the adult doesn't. If the probability is 0.69 that an adult has the seatbelt, which is equivalent to 69%, then the probability an adult does not have on a seatbelt is going to be 1 minus 0.69, which is 0.31. And you want to fill that in, okay? So the first thing that occurs is either the adult has a seatbelt on or the adult doesn't. Notice that those add up to 1. Okay, now we're going to consider, all right, the world where the adult is wearing the seatbelt. So based on the condition that the adult is wearing a seatbelt, up here it told us 66% of the time a student will be wearing a seatbelt. So the probability that a student wears a seatbelt given that the adult is wearing a seatbelt is 0.66. So this is the probability a student is wearing a seatbelt given that the adult is wearing a seatbelt. Now, the only other option is that the student does not wear a seatbelt, given that the adult wears a seatbelt. So we get that by doing 1 minus 0.66, and we get 0.34. Now, we were also told that in the event that an adult does not wear a seatbelt, the student is only 26% chance likely of wearing a seatbelt. So the probability that a student wears a seatbelt given that the adult does not is 0.26. So the probability that the student follows the example of the adult there is going to be 1 minus 0.26, and it's going to be 0.74. Okay, so we're going to use this to determine the probability in general that a high school student wears a seatbelt. So let's look at our outcomes here. We have an outcome right here where the student wears a seatbelt given that the adult wears a seatbelt, and then we have one down here where the student wears a seatbelt given that the adult does not wear a seatbelt. So these two branches that lead us to event C are going to be included in our answer. Okay, so our probability of event C occurring, the student is wearing a seatbelt, is going to be the probability of A and C plus the probability of B and C. So the probability of A and C is going to be the probability of A times the probability of C given A. So that's going to be our 0.69 times 0.66, and then we're going to add to that the probability that the adult does not wear a belt times the probability that the student does wear a seat belt given that the adult does not. So 0.31 times 0.26. And when we multiply and add, we get 0.536. So when you're figuring out probabilities, if you want to figure out the probability of A and C, you multiply down the branch, okay? If you want to find the probability of B and C, you multiply down the branch. And then to get all the probabilities that lead to C, you add the branches together. Okay, so go ahead and do the guided practice based on that example, and we will go over that in class next time. All right, and also do the one on about the high school basketball. All right, guys, that is it for our 10.5 lesson. I will see you in class.